Welcome to the Macrosystems EDDI module, Exploring Trade-Offs in Water Quality Management Using Environmental Data. This module has been developed in collaboration by water treatment instructors at Mountain Empire Community College and freshwater scientists at Virginia Tech. The module is part of the Macrosystems EDDI program, which stands for Environmental Data-Driven Inquiry and Exploration, and is supported by a grant from the United States National Science Foundation. This module includes 3 activities, which are all designed to introduce concepts related to assessing water quality and collecting high-frequency water quality data. In Activity A, students will explore how disinfection byproducts are formed during the drinking water treatment process and examine trade-offs between disinfection and byproduct formation. In Activity B, students will view and interpret environmental data that can indicate when naturally occurring DBP precursors are present. In Activity C, students will make water treatment decisions using environmental data that can indicate when DBP precursors may be present. All of the activities are designed to address the focal question for this module, which is, how can we use environmental data to inform our understanding of the trade-offs involved in water management decision-making? Today, we will focus on the trade-off that can occur between chlorination, an important step in the water treatment process to remove potentially harmful pathogens, and the formation of disinfection byproducts. Disinfection byproducts, or DBPs, are compounds that are unintentionally created during the drinking water treatment process. Many of them are known to be carcinogens or capable of causing cancer. There are dozens of different DBP compounds. 2 common classes of DBPs are trihalomethanes, pictured on the bottom left of the slide, and haloacetic acids, pictured on the bottom right. Disinfection byproducts form when DBP precursors, which can be organic matter or inorganic compounds in drinking water sources, react with chlorine during the disinfection process. Organic matter is derived from living organisms and contains carbon. Inorganic matter may also contain carbon but is not derived from living organisms. When DBP precursors, such as naturally occurring organic matter, react with chlorine during the treatment process, DBPs may sometimes form. DBPs are monitored by water sampling. Once a quarter, water samples from both treatment plants and distribution systems must be tested for a range of DBPs. In addition, raw and filtered water are tested once a month for total organic carbon, or TOC. High TOC levels can indicate the presence of DBP precursors, which may form DBPs during treatment. Some forms of organic matter can be measured using sensors deployed in a drinking water reservoir. We can develop a relationship between these sensor data and total organic carbon, or TOC, to determine when DBP precursors might be present. If precursors are present, we can adjust treatment processes to mitigate DBP formation risk. In this way, environmental data can help us avoid the formation of disinfection byproducts. Today, we are going to explore environmental data from drinking water reservoirs in Southwest Virginia, and then use that data to explore trade-offs in drinking water treatment decisions. For example, some of the data are collected using a YSI EXO sensor, which is pictured on the bottom right of the slide. This sensor is deployed at a fixed depth in the reservoir, attached to a catwalk. In this module, you will work with fluorescent dissolved organic matter data collected by this sensor. FDOM stands for fluorescent dissolved organic matter. Characteristics of FDOM are, first, it is derived from living things, like tree leaves or phytoplankton, and contains carbon. Second, FDOM compounds are not particles, but are dissolved in the water. And third, if light is transmitted through the water, these FDOM compounds will emit their own light in response through the process of fluorescence. One everyday example of dissolved organic matter are the coffee compounds that dissolve from the coffee grounds into the water and turn the coffee brown. FDOM is measured using sensors that transmit light at a particular wavelength through the water and then measure how much light is emitted from the fluorescent organic matter compounds in return. Because it is a form of organic matter, the presence of FDOM can also indicate that DBP precursors are present. Thus, higher FDOM may mean an increased risk of DBP formation during the treatment process. You will have the option to explore FDOM data from one of two reservoirs located in Southwest Virginia, Falling Creek Reservoir or Beaver Dam Reservoir. Both reservoirs are located in Vinton, Virginia, near Roanoke, and are owned and operated by the Western Virginia Water Authority as drinking water supply reservoirs. You will use high-frequency FDOM data from your chosen reservoir to assess the risk of DBP formation and make water treatment plant operation decisions. In Activity B, you will convert FDOM to total organic carbon to assess when DBP formation is most likely in your reservoir. In Activity C, you will complete a drinking water reservoir case study and view FDOM data from different times of year in a reservoir. Then you will decide whether to enact additional treatment measures to avoid DBP formation during the treatment process. This module has 4 learning objectives. First, to define what disinfection byproducts are. Second, to describe the environmental and water treatment processes that influence the formation of disinfection byproducts. Third, to understand the trade-offs between disinfection and byproduct formation that can occur when chlorinating water, and treatment techniques that can be used to manage these trade-offs, such as coagulation or activated carbon filters. Fourth, to use environmental data visualizations to identify when additional treatment techniques to avoid disinfection byproduct formation should be used to meet water quality objectives. I will now give a brief overview of the module activities. In Activity A, you will complete 2 objectives. First, you will learn about factors affecting DBP formation and drinking water thresholds for DBPs. Second, you will explore trade-offs in disinfection versus DBP formation. In Activity B, you will learn more about the focal drinking water reservoir that you select to work with during the module. Then you will view and interpret organic matter data from your focal reservoir. In Activity C, you will complete a scenario which asks you to make water treatment decisions using organic matter data. The module can be accessed through your course Canvas site. You will complete module activities in an R-Shiny app, which is an interactive website. Be sure to complete the Quick Start Guide to the module and watch the video that explains the interactive module features. Questions are embedded in the app, and you will answer these in a Canvas quiz. Thank you so much for participating in Macrosystems EDI Module 10.